So we're going to think today about quadratic expressions. And as always, my ideas I hope will be interesting. Might even be inspiring. They might use your students. I think, as I always say, but I'll not say it again. If you try anything and it works, do let us know. Do share in the chat if you tried any of these ideas out, tried any of these activities out, and they've worked successfully. Please do let us know. But also the other way around, if you try something that doesn't work, quite interesting to know that. Obviously, I'm sorry if that's the case, and you can perhaps share with us why you think it didn't work. Quadratics might seem like sort of strange thing to choose. After all, complete square, you factorize, kind of what else is there to it? And in a sense, you're right, because that's what we're going to focus on. We're going to focus on completing the square, factorizing, solving, and think about what this looks like, what this means for the graphs, and what the graphs look like. But when I was putting this together, I kept coming back to that quotation there in the speech bubble: "Teach the little that leads to a lot," which I think is from Gattegno, Caleb Gattegno, the educational theorist, inventor, I think, of Cuisenaire rods. Those of you who remember using those perhaps yourself when you were a young child, or maybe if you have children yourself, they've come across them in primary school. And so Gattegno, someone once told me this quote came from him, and I always attribute it to him. I don't know if it's true actually, but it's a jolly good quotation wherever it comes from. And I think this is a really good example of it. So I'm going to go through lots of activities with you and suggest what things you could do, but I'm not for one moment suggesting that what you should be doing is doing an example of each. I think really it's you show them how to complete the square in a simple case, and then you give them the more complicated examples and get them to work it out, get them to have that productive struggle, to engage with that desirable difficulty. I.e., you show them the little, this is what we mean by completing the square, and it leads to a lot. I'm going to try and show you where I think the lot might go to. And simply factorizing, well, factorizing is really straightforward. When we come to the harder examples, I'm not suggesting you go through these examples with them. You just say, look, you know how to factorize, take what you know and apply it to this unfamiliar situation. And if you think of the language in the national curriculum, it talks about routine and non-routine problems. And I think the key thing is not to teach them how to do the non-routine problems, but just to give them the non-routine problems and respond to what they do, how they react, how they respond to the problems as they grapple with them. Last week we talked a lot about probability, and the reason I want to do that with you was because it seems to me that students often have fluency but not understanding around probability. I think this week the focus is more on fluency. We're going to get them really good at completing the square, at factorizing quadratics, at solving equations. So really kind of focusing on the fluency or the I know how aspect of it. There will, of course, be some understanding aspects and some factorial aspects being developed. But this to me is, I wish I could snap my fingers. Working with quadratics is a snap. It's a thing that high attaining students need at their fingertips, particularly if they go on next year. So, to study maths and ideally indeed further maths, we really want them to be not to be phased by an unusual completing the square, by a disguised quadratic, a quadratic in a hidden form. By coping with sort of surds, manipulating surds as though they were integers, so not being thrown by the fact that they're surds. So that's my focus here. The idea is very much about success now and success in the future. And I think lots of work on algebra now in year 11 does have GCSE benefits, but I think it also has some really significant A-level benefits. So you really want your students to be familiar with these. So you really want to make sure they can tell you straight away that this is a squared and either add or subtract to ab or b squared, and tell you straight away that that factorizes into a subtract b, a add b. So I'm just letting somebody into the room, sorry. And then this one's a little bit harder. It is a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ac, or indeed perhaps even 2ca, to keep the pattern going. And the way you remember it is, if it was a plus b all squared, it'd be a squared plus b squared plus 2ab. If it was b plus c all squared, it'd be b squared plus c squared plus 2bc. And if it was a plus c squared, so it's kind of all of those put together. A squared, b squared, c squared, 2ab, 2bc, 2ac. I've always been a fan of sort of area representations of multiplications. So I've always been a fan of, say, this, writing this as A, B, B, because that explains, that reminds us where we get the 2AB from. And of course, you can do exactly the same thing here. It's just now a 3 by 3 grid. So here we've got A, B, C, A, B, C. And so you've got the A squared, B squared, C squared along the main diagonal. And then you've got the A, B, and the ACAC and the crikey, what's happened there? That's what I want to do, and the BC and the BC terms there. And what I quite like about it is the grid shows that we've got 9 terms. We're expecting 9 terms. Have we got 9 terms? Yeah, we've got 1, 2, 3, a squared, b squared, c squared, and we've got 2 AB, 2 BC, and 2 AC. So we have got 9 terms. We've got 3 and 6 to make the 9 terms, and that's just kind of a good little thing to get them to check. How many terms are we expecting? It's a 3 by 3 grid. Have we got the right number, etc. So they need to be really good at this, otherwise they're not going to be very good at the rest of it. So complete the square. Well, tell you what, over to you. I'm going to give you a couple of minutes. Do you want to complete the square in of those? The first one is obviously straightforward. X plus 3 all squared, subtract 8. Now the second two, I know perhaps what we might do. We might factorize the 4, factorize out the 2, but I don't think the students would do that. You know, so how do you, so if all you taught them to do was the first example, what do you think how do you think they'd go about doing the second example? How could they extend by themselves, teach the little that leads to a lot, how could they extend by themselves the principle of the first equation, of the first simplification, the first expression, complete the square in the first expression, and apply it to the second and the third example? Just have a little think about that. I'm just going to give you a little moment to think about that. If you just put this in front of your year 11s, so what would they do? Perhaps don't share anything in the chat just yet. Just hold on for a moment. And in particular, what do you think they would do going from the second to the third example? So I mean, Amy, I think you're right. I think they would divide by 4 because they think it's an equation even though it's not. They're going to divide both sides by 4 and they'll kind of write it's x squared plus 1.5x plus 0.25 or something like that. So they would divide by 4 even though they can't, because they can't divide both sides by 4 because there aren't both sides to divide by. There aren't 2 sides to divide by. So I think that's a really good point, Amy, to really be on the lookout for that. I'm not asking for anything, Harvey. I'm asking you what you think your students would do if all you taught them how to do was the first example. So I think all the various suggestions coming through, I think Claire, you're right. I think what I would like them to do is I'd like them to say, well, look, the point about completing the square is you find a bracket which squares, and then you adjust it at the end. So I think they might look at the 4x squared and try 2x. And you're probably right, Claire. They probably would try it because it's half of 4. And obviously what you want pinned down really is not half of 4, it's the square root of 4. And that's why 4 is a nice example, because they say half, and you say, is it really half? And no, it's the square root that's important. So listen, you listen to what they're saying. And then I think what they would do is I think they'd put the 3 in first of all. I think they did 2x plus 3 because they saw 3. They basically changed the x to the 2x because it's x squared, not 4x squared. And then they'll put the 3 in because it was 3 last time. And then what you want them to do is then go, well, okay, let's just expand that. Is that right? So you want them to be thinking, well, so what does this give me? This gives me 4x squared plus, and that's why knowing that example, that simplification, that expansion at the top is so important. Because you want them to say it's going to be 4x squared plus not 6x plus 12x plus 9. Oh, that's not very handy. I don't really want 12x there, do I? So, okay, so you don't want 12x, then what's causing the problem? The 2x, but you need the 2x to make the 4x squared. So if you're not going to change the 2x, what else can you change? If I can change the 3, what can you change it to? And they won't like this, but they'll eventually realize to change it to 1.5. And that's the value in the activity. The value of the activity is not the answer. I don't really, within reason, I don't really care what the answer is. What I care about is the thought process they've gone through. Why did I change x to 2x? What's the effect of that? 3's not right. What do I have to have there instead? Oh, less than that. How much? Half of that. Oh, right, 1.5. And then, of course, the 1.5 squared. And you're going to get 1.25 as an answer. Be on the lookout for that. If you ask them to square 1.5 or 1.5 squared, you will get 1.25. because 1 squared is 1 and 0.5 squared is 0.25. So, you know, if you don't believe me, try it, see what happens. So that's 2.25. Then we subtract 1.2, sorry, 1.25, sorry. We subtract 1.25, 1.25 to get that correct. Okay, and it does help you write, Doug, it helps write it as 3/2. But again, you want them to tell you that. You want them to say, wouldn't it be better? You want them to say, surely I can write it as 3/2, because 3/2 then is 9/4. I bet you get 6/4 though. 3/2 squared is 6/4 because that's a very persistent error as well. So then when you come to the third example, you want to say, well, okay, well, what are you going to do here? Now, I know what we would do. What we teach them to do is take out the factor of 2, or take out a factor of 2. But we're not trying to teach them. We're trying to get them to adapt and extend. So why did you use 2x there? Because 2x squares to give me 4x squared. Exactly, sorry, Claire, I was just distracted by what you wrote in the chat. Yeah, exactly. Yeah, so what you want them to do, Amy, you're right. What you want them to say is, well, can we not try root 2x? So you want them to make the progression from x to 2x, and then from 2x to root 2x. Okay, so why did you try that? Oh, because that squares give me 2x squared. Okay, and then what you're going to have there, what's that going to be? And you want them to think through, well, what I need is, I'm going to get 2, whatever that number is, 2 lots of that has to give you my 6. 2 lots of that root 2x has to give you my 6x. And then obviously we don't need to worry about the x too much, look at the coefficients. And then, so what's the number going to be? It's going to be 6 over 2 root 2. So it's going to be 3 over root 2. And so you want them to come to the realization that the question mark has to be, or sorry, the box, the empty box has to be 3 over root 2. And then, okay, so what happens when we square 3 over root 2? We get 9/2, which we don't want. So we need to take off 3.5, and 9/2 is 4.5, so to take off 3.5. Now, I know they could do that more efficiently. I know we can say, look, take out the factor of 2, and et cetera, but that defeats the struggle, that defeats the desirable difficulty. So I would say, don't tell them what to do, get them to work it out. You know, someone will do it one way, someone will do it another way. Somebody might even say, look, we're not to write as 2 lots of x squared plus 3x. Get them to share and compare their different answers and see what happens. That, in a sense, that slide is the key slide for today. It's to teach the little, that hopefully leads to a lot. That's the idea behind it. Okay, over to you. Couple of minutes. Do you want to do those? And just a bit of practice. Don't put anything in the chat yet. Don't put anything in the chat yet. Just a moment for you. We're going to come back to these expressions later, so it's probably worth just having a look at them now. And be thinking about the progression, thinking about the variation, the procedural variation. You can see there's a lot of squares and 6s and 1s floating around. First one should be straightforward: x squared plus 3 all squared subtract 8. Second one, now obviously I know that's not hang on, sorry Claire, go back. No, I subtracted 3.5, Claire, because I want to end up with 1 at the end. So when I square 3 over root 2, that gives me 9/2, which is 4.5, and then I subtract 3.5 so that I end up with the 1 at the end. This one, by the way, I wrote it as sine in brackets. I know it should be sine squared x. I know higher maths it's sine squared x, but I just think that's an unnecessary notational complexity. So I would leave it like that, and so I'm going to get sine x plus 3 all squared, take away 8. And thoughts about the last one? Yeah, yes, Helen. I agree. That's what I thought. Helen agreed. Third one. Suggestions for the third one? Again, Harvey, we might, but that's not what we want them to do. You know, we want them to square a bracket and then take something away. So we've told them that complete the square means write a bracket, square it, and take away or add on a number. That's what complete the square means. It means square a bracket and adjust it with a constant, either add or subtract a constant. So that's what we can draw out from the previous examples, is what's the same, what's different. In each case, we've got a square bracket, a bracket which has been squared, sorry, add, or in this case, actually always subtract a pure number. And that's what we're doing here. That's what complete the square means, yeah? Yes, so we certainly could do it like that. I mean, I think definitely using root x is a good idea. I was thinking of this. I was thinking of that, because that gives me x, that gives me 1 over x, and then my cross term would be 2 lots of, the 2ab term would be 2 lots of x, 1 over x, sorry, root x, 1 over root x, which is just 2. And so then I think I need to add on 4 at the end, don't I, to get the 6 in total? Yeah, I think it's the 4 at the end, because the cross term, the 2ab will give me 2, and then there's a plus 4. And so we can see that, again, that what's the same, what's different, what's the common theme? The common theme is we've got a square bracket, or bracket that has been squared, and then the adjustment is only a constant, it's only a pure number. So if that's the idea of complete the square, how do we do these? So if the idea of complete the square is have a square bracket and then add or subtract a pure number, what about these ones? You say to them, sorry, that's like a slight tone of wonder. I'm not saying it to you like, oh, mystery. Oh, no, I know you can do them. Go on, I'll give you a couple of minutes to have to think about these. Not yet. Control yourself, Harvey, not yet. But by all means, what I say to my students is, by all means, line it up in the chat. I mean, write it in the chat, but don't press send. We do what's called a chat blast, where I give them a countdown and they have to put all the answers in the chat, and then they can press the send, then they can press enter. So if you want to put an answer in, that's fine, but don't send it yet. So a couple of minutes to think about these. Remember, the principle is it's a single bracket squared, and then all I want at the end is add or subtract a number, an x or indeed y free number. And hopefully you can see how this is, how the little has led to the lot. This is hard. Thanks, Ben. It's not my idea. Remember what I said. Anything which is good comes from somebody else. I can't remember where I got it from, but someone I'm working with at the moment that suggested. I thought, yeah, that's a really good idea. But please giving it a name, the idea of a chat blast. And so yeah, sort of. Okay, do you want to put, if you want to, do you want to put any answers you've got in the chat, but don't press send yet? If you want to. I said don't press send yet, Xavier and Harvey. God, you're worse than year 9. However, I am in some agreement. So this, I think, is x plus y plus 3 all squared, take away 8. This is x squared plus 2x plus 3 all squared, take away 8. And this is 2x subtract 3 all squared, also take away 8. Now, so you can see how there's a bit of a theme going on here. There's got a bit of taking away 8 happening. And of course, how I make them up is I start with the bracket, I square it, and I do subtraction. So I start with the completed square and work backwards. How do you do these? How do your students do these? Well, partly because if they know that bottom identity, if they know they're going to do that at the bottom, they're looking for, hang on, so I've got some squares and I've got double, double, double. Oh, okay, right. So that 6x, that 6x and that 6y has come from double something, oh, double 3. So I'll try x and y and 3. This one's obviously harder, but they're thinking, well, look, I've got x power 4, so let's start with an x squared. X power 4, let's start with an x squared. So maybe it's x squared plus something, but if I had x squared plus a number, where would I get the x cubed from? So they've got to play around, they've got to try something. There's no point in trying anything too big, because if that was sort of, say, 3x or 4x or 5x in the middle, you get at least 9x squared, 16x squared, or 25x squared, which we haven't got. We've only got 10x squared. So the coefficients can't be that big in the bracket, because the coefficients aren't that big in the answer, in the expanded bracket. So there needs to be an x term, otherwise where do you get the x cubed from? But it can't be a huge x term, a huge coefficient of x, otherwise you get a very large coefficient of x cubed and then indeed x squared in the answer. So it's that kind of playing around that you want them to do. I put the last one in because the reasoning that 4 to the x is it's 2 squared to the x, which is 2 to the 2x, which is 2 to the x all squared. My experience is that's something children find really hard. And I'm not totally surprised, it is difficult. So 4 to the x is 2 squared to the x, which is 2 to the 2x, which is 2 to the x squared. Because they don't really believe that when you have a power raised to a power, you multiply the powers. They really want this to be 2 to the x squared. They don't really want it to be 2 to the 2x. So I put that in so that they have to think quite carefully about, well, how can I complete the square? It's not even a quadratic. Oh, it is a quadratic because it's 2 to the x squared. So it's a quadratic in 2 to the x. So that's why I put that one in, because I want to rehearse that algebra, that, as I say, that 4 to the x is the same as 2 to the x all squared. Okay, so what do we do with completing the square? We can find minimum values. So, for example, the first one, we know we've got x plus 3 all squared, subtract 8. And so the minimum value is going to be -8 when x is -3. Now that argument is not an easy argument. I find I need to do it a lot of times with year 11s and indeed year 12s and year 13s. The argument that that's a square number, and therefore, as long as x is real, which is what we think at the time being, as long as x is real, that is greater than or equal to 0, it's a positive, and therefore, no matter what it is, when we take away 8 from it, we can't go lower than -8. How low can you go? We can only go as low as -8, because the thing I've coloured in, I've just highlighted, can't go lower than 0. And when do we get to -8? When the green thing is 0, i.e. when x equals -3. I think that argument needs a lot of repeating and a lot of rehearsing. What about the second one? Well, the second one we said earlier was √2x plus 3 over √2 all squared, subtract 3.5. And so the minimum value is -3.5. And it happens when, oh crikey, when that bracket is equal to, so we want the bracket to be 0. We want that to be 0, and so x has got to be -3 over √2 over √2, which with a bit of work turns out obviously to be -3 over 2. Again, think of what that manipulation of the bracket. And yes, it probably would make sense how to actually write the equation. You probably do need to. You're right. X √2 equals -3 over √2. But then what they're going to do is they're going to write -3 over √2 over √2. And then I bet what they then do is then they cancel the √2s or something like that. So there's lots here to be done about just a little bit towards the end of solving to find the value of x, which makes the bracket minimal. And then we come to the last one, the third one. We get off straightforward enough. So it's x squared plus 3 all squared, subtract 8. And so the same thing is minimum is going to be -8 when, oh, hang on. No, it's not. So we get that productive struggle, because I can't make that equal to 0. It's not possible to make that equal to 0. in fact, what can I do? The best I can do with it, or the least I can do with it, is make it 3. Amy, good question. Can I come back to that in a moment? Sorry, Amy. So the least I can do with this is make it equal to 3. So that isn't the minimum. The minimum is 1. The minimum is 1 when x is 0, because x squared plus 3 is always at least 3, and so the square bracket is always at least 9. And so the minimum value is 1. And I think that sort of pulling up sharp, that handbrake turn as they come to that question, is what makes the value of the question. Sorry, Amy. How do you stop them? Well, no, I'm happy. So Amy's asking about, as you can see in the chat, Amy's asking about sort of stopping them doing that. I don't want to stop them doing that. What I want them to do is not then cancel the root 2's. So I want them to think what this means is -3 over root 2 divided by root 2 over 1, and then go from there. Okay. I mean, that would be nice, Harvey, but I don't think they're going to do that. They're going to divide both sides by root 2, because that, if it was 5x, they divide by 5. So root 2, they divide by root 2. I mean, I suppose they might rationalize the denominator first, but then which denominator are they going to rationalize? So I want them to write it as divide by root 2 over 1, i.e. multiply by the reciprocal, multiply by 1 over root 2, and then go from there. That's probably what I would be encouraging them to do. Okay, so what about this one? So what did we say earlier for this? So we wrote this as sine x plus 3 all squared subtract 8. So same argument, it said minimum is -8. No, it's not, because I can't make sine x plus 3 equal 0, because I can't make sine x equal -3. Now, by this point in year 11, they ought to know what the sine graph looks like. So they ought to be aware of the sine graph looking like that, being bounded between 1 and -1. Oh, so this one's quite interesting, actually, because not only does it have a minimum, it also has a maximum, actually. So what can we say about this? Well, sine x is between 1 and -1, so the most it could be is 1 plus 3, obviously 4 squared, take away 8, which is 8, and the least it could be is -1 plus 3, which is 2 squared, take away 8, is -4. Which, yes, sorry, Claire, going back to that previous question, yes, so multiplying both sides by root 2 would make life nicer in the first place. I agree. And that's the kind of discussion to have. The point of this question is not so much what's the answer, it's how do you process it. Sorry, the question in the middle. The point of the question in the middle is not so much what's the answer, but how do you get to an answer? What do you do? So the suggestion here being maybe multiply when you're trying to solve that equation equals 0. First thing to do is multiply both sides by root 2. So then you get 2x plus 3 equals 0. That would be really nice. I agree, Claire. Thank you. Okay, what about this one? Well, when we completed the square, didn't we? What did we get for it? We got, back in the chat somewhere, where was it? Oh yeah, x squared plus 2x plus 3. Yeah. So this one we said was x squared plus 2x plus 3 all squared, take away 8. So what's the minimum? Oh, well, the minimum is going to be -8 when what's in the bracket equals 0. But what's in the bracket doesn't equal 0, because if I complete the square on that, I get x plus 1 all squared plus 2 squared, take away 8. So complete the square on the quadratic inside the bracket. So I get x all squared plus 2, and then all squared that, take away 8. So the minimum is going to be when x is -1, I'm going to get -1 plus 1 is 0, and then 2 squared is 4, and then take away 8 is -4. So the minimum is -4 when x is -1. And again, it's the thinking through of that, which is what the value of the activity is, not so much the answer. It's trying to make that quadratic equal 0. Oh, I can't. How do I know? Well, the discriminant is negative. The b squared subtract 4ac is negative. And so therefore, what can I do? I can complete the square. So I can complete the square within a completing the square. And then the last one we said was 2 to the x, take away 3 squared, take away 8. So can I make this equal -8? This time I can. This one I can get a minimum value of -8. But when x equals, well, 1 point something, how do I know it's 1 point something? Because 2 to the 1 is 2, and 2 to the 2 is 4. So presumably 2 to the 1 point something is 3. And you're right, Harvey, it sets up the idea of logarithms at some point in the near future. I think you mean 2 to the 1 rather. I mean, you're right, Harvey, that 1 squared is less than 3, but I think you mean 2 to the power 1, not 1 to the power 2. So here we can get the minimum, but we don't really know where it is. It's at a number which is not really nice. You could perhaps use trial improvement to try and find out what that number is. Okay, so then we can go even further. Right, so now can we complete the square with expressions like these? So what have we got? Well, I've got an x squared and a 6x. So maybe I've got an x plus 3 all squared. I've got a y squared and a 10y. So maybe I've got a y subtract 5 all squared. And that would give me 9 and 25, which is 34. So I need another 16 to make it up to 50. So I look at it, I sort of chunk the terms together. X squared and 6x, x plus 3 all squared, y squared take away 10y, y subtract 5 all squared, and then I've got 16 left over. So what's my minimum? My minimum is 16 when x is -3 and y is 5. I need to have 2 values to hit the minimum. And so then here, well, oh look, I've got an x squared take away 2xy, and well, I've definitely got 1y squared. So let's start off with x take away y squared, and then that leaves me with another y squared and an 8y, so a y plus 4 all squared, and then that will give me 16, and then I therefore want another 4 to make 20 in total. So I've got x squared, -2xy, and a y squared, and another y squared, and an 8y, and a 16, and a 4, and that altogether makes 20. Right, so my minimum is 4 when y equals -4, that makes that bracket equal 0, and x equals y, because that makes the first bracket equal 0. Oh, right, so therefore x has to be -4. So at -4, -4, that expression will equal +4, which is the minimum value. And then last case, well, what can we see? We can see an x squared and a 4z squared and a 4xz. So that suggests to me x plus 2z all squared. And then I've got a 3y squared plus a 12y. Well, let's do what we did earlier. So let's write that as √3y plus something squared. Right, so what's the something going to be? So 2 something √3 has to equal 12 is what we're thinking. So we're thinking 2 lots of something √3 has to equal 12. Think about the coefficients of y. So it's going to be 6 over √3, say. So 6 over √3. And when I square that, I get 36 over 3, which is 12. So I need to subtract 12 because I've got no number at all in the original expression. So they're building it up bit by bit. And so what's the minimum value? What is the minimum value? The minimum value is going to be -12 when y equals -6 over 3, i.e. -2. And x, well, x and z can be anything as long as x equals -2z. So the reason why I chose this example is because this gives you a value for y. Y has to equal -6 over 3 and -2. And this gives you a relationship between x and z. X has to be -2z. So the first two have unique minima. The second one does not. The third one does not have a unique minimum. It has a whole family of minimums where y equals -2, but any pair of values x and z, as long as x equals -2z. So you're getting different behaviours happening, despite given the equations, the expression that you've got. Okay, solving then. So let's crack on and solve. How do we solve? Oh, just complete the square. So the first one is nice and straightforward. So we've got x plus 3 all squared, subtract 8 is 0. And so we get x is -3, add or subtract √8. Fine, no problem. What about the next one? So do the exact same thing, complete the square. And so we're going to get x squared plus 3 all squared, subtract 8 is 0. And so we get x squared is -3, add or subtract √8. Oh, problem. Because -3 is less than √8, or indeed negative √8. So -3 plus √8 is itself a negative number. So I can't solve that in the reals because -3 plus √8 is 0. Oh, and obviously -3 subtract root 8 is less than 0, but -3 plus root 8 is less than 0. So just a tiny change has made the equation insoluble. What about the next one? So we complete the square on that. So we get x plus 1 over x all squared plus 4 is equal to 0. And so we get that root x plus 1 over root x all squared is -4, which again, contradiction, I can't do. I can't have a square number equaling a real square number equaling -4. But before we move on, notice that that equation is the same as that equation. I've just rearranged, I've just divided 3 by x. So rather weirdly, I sort of thought about this the other day, and it's still, I'm happy with it mathematically, but I'm still a bit sort of perplexed, or not, I'm still a bit startled by it, that a soluble equation I can solve, has been transformed perfectly legally into an equation I can't solve. And that's quite startling, I think. The idea that by manipulating the equation in a fairly straightforward way, divided by size by x, I'm not doing anything crazy with it. I've turned an equation I can solve into an equation I can't solve. So on that bombshell, I'll leave you to think about that. And you might want to check, by the way, that these solutions do. These are the solutions of this equation, and they are. So the question is, how do you get them? How does this yield the solutions x equals -3 add or subtract root 8, which really are the solutions? And of course, the resolution is you have to go into complex numbers. And so that's why it's quite a nice thing to do with your students, tell them, you know, this is why we need complex numbers, because sometimes to solve real equations, we have to step into the complex numbers, solve in the complex numbers, and then bring that solution back into the reals. And then I quite like things like this. So x to the 6 plus x subtract 3 squared plus 1 is 0. What are our thoughts about that? Again, problem contradiction, because x subtract 3 all squared is positive, x to the power 6 is positive, and then plus 1 will make it more than 0. So you can't, so that has got no solutions. I'm a big fan of Diophantine equations. Diophantine equations, as you may recall from your own education, are equations which have whole number solutions, which have integer solutions. That's what we're looking for, integer solutions. So I'm looking here for an integer n, such that n squared plus 20n plus 11 equals another integer m squared. So what should I do? Well, let's complete the square. So n plus 10 all squared subtract 89 is m squared. And so n plus 10 all squared subtract m squared is 89. So two square numbers that differ by 89. Well, I can play around for a bit of trial and error, but that's not very helpful. So what I need to think is, aha, this is the difference of two squares. So the left-hand side is just n plus 10 subtract n, and n plus 10 plus m. And the right side is 89. And then the thing about 89 is, it's prime, and I'm looking for integer n and integer m. So I'm looking for integer solutions. That's what the word Diophantine means. So I'm looking for whole number n and whole number n, possibly negative as well. So integer n, integer m, and they're going to multiply together to make 89. Well, there aren't many options for that. My only options are n plus 10 subtract n and n plus 10 plus m. Well, either 1 and 89 or 89 and 1. Those are the only possibilities. Because I've got two factors making 89, but the factors have to be integers. So I want two integers that multiply to make 89, and there aren't many of them. There's only 89 and 1 and 1 and 89. And so just finish. So now it's simultaneous equations. So if I add them together, I get 2n plus 20 equals 90. So I get 2n is 70. So I get n is 35. And if n is 35, then 35 plus 10 is 45. Take away 44 makes 1. So I'm going to substitute that up there. And then that's going to give me that m is 44. And then the other way around just gives me the same. Okay, because it's just now, actually what happens is I get negative. So I get n is 35 and I get m is negative 44. And obviously that makes sense because 44 squared and negative 44 squared are the same. So I get only one, so surprisingly, there's only one pair of square numbers. So there's only one value n, which makes this a square number, and n is 35, and the answer you get is 44 squared. So Diophantine equations are really lovely, and we're going to come back to them. They're so lovely, we're going to come back to them later as a trailer for the second part of the session. So factorizing. I'll give you a couple of minutes. You want to factorize those? They do all factorize. They possibly, you might not think they do. So factorize fully. Nothing in the chat yet. I'm just going to slurp my coffee. Sorry. I probably should stop my video actually. You can admire my Blackbird and Bramble mug. It's called. Well, as always, I'm going to do the easy first example. So I'm pretty sure that's x plus 2, x take away 4. So therefore, by extension or by generalization, that's going to be x squared plus 2 and x squared take away 4. Job done? No. Because that, of course, they need to recognize as being the difference of two squares. So you really want your students, your year 11s, or your year 10s at the right junction, to be on their toes for the difference of two squares. Always, always, always be looking out for the difference of two squares. It's so, so useful. So you want to go, right, that's x squared plus 2, x take away 2, x plus 2. What about the next one? Well, the next one, sir, doesn't factorize. It's x take away 1 all squared and then take away 5. Doesn't factorize. Except it does, because 5 is a square number. 5 is root 5 squared. And so once again, I've got the difference of two squares. So it does factorize depending on what I'm allowed to have in the bracket. Yeah, exactly. That's exactly what I was fishing for. Yes, thank you. X take away 1 take away root 5, x take away 1 plus root 5. And so this idea of factorizing is we kind of say it does or doesn't factorize. Well, it depends what you're allowed to have in the bracket. And if you're allowed to have root 5 in the bracket, it does factorize. If you did maths degrees at university, this may ring a bell. We're talking about what's called the splitting field. And so we can split it over the field of z root 5, integers of root 5 chucked in. So that's, I quite like that, just making them realize they can factorize more than they thought they could. And simply this one, well, they could just try to factorize it by some sort of method of multiply to make, add to make. But again, let's try a difference of two squares argument. So what is this? It's x take away root 2 all squared, because that gives me the 2 root 2 for the cross term. And then it's plus root 2 take away, plus 2 take away 18 will give me 16. So by my difference of two squares factorization, that's going to be x take away root 2 take away root 18 and x take away root 2 plus root 18. But root 18 is 3 root 2. So actually what I've got here is take away 3 root 2 and add on 3 root 2. And so what I end up with is x take away root 2 take away 3 root 2, which is x subtract 4 root 2. And then x subtract root 2 plus 3 root 2 is x plus 2 root 2. So I complete the square, get a slightly unpleasant answer, factorize it, and then actually, well, because of the numbers I chose, the factorization makes the answer much simpler. So it does factorize exactly, again over the root 2 splitting field, over the z root 2 splitting field. It does factorize, and we can get to it by first completing the square. And this, this point about difference of two squares is so important. So you want them to look at that and go straight away, okay, so what's that? So it's x squared subtract 4y squared, x squared plus 4y squared. Oh, and that I can then factorize further. So it's x subtract 2y, x add 2y, and then x squared plus 4y squared. And they'll be on a roll, so that they will now try to factorize x squared plus 4y squared, which write them more clearly. They'll now get so carried away, they'll be convinced that they can factorize x squared plus 4y squared. And let them do so, let them try, let them see if it works. Don't tell them they can't. The great thing about factorization is you can't get it wrong. Just try it. If it works, it works. If it doesn't, it doesn't. And the next one, so clearly we want to think of, look, that's 3 lots of x plus y, subtract 2 lots of x, subtract y. And then it's 3 lots of x plus y plus 2 lots of x, subtract y, etc. And what some of them will do is they'll multiply the brackets. So the first thing they do is try and expand the brackets. Why are you doing it? Why expand the brackets? Once you've got, say, 5x squared and 5y squared, you've completely lost the difference of 2 squares structure. So you don't want to multiply the brackets. The multiply the brackets will mask, will hide what is going on. And then obviously the next two, you want to think about, well, you want to think about what are the possibilities? So could it be x squared and y squared? Well, no, because then that would give you y to the power 4, which I haven't got. And then here, is it going to be something involving, sort of say, x cubed and x cubed? Well, unlikely, because with x cubed and x cubed, then I'll probably have some x cubed terms in here. I've got no x cubed terms whatsoever. So getting to realise that, what are the possibilities for the terms and the factors, and then checking and expanding and actually checking, is that actually right? Do they actually get the terms and the factors? Do they actually get the product they need from the factors they have chosen? Is this right? I don't know. Have you found it and checked? No. We'll go and expand and check it, and then come back and answer the question. Right, I'm going to leave that for you to think about. That's my absolute favourite, my all-time favourite factorisation. And yes, I do have an all-time favourite factorisation. It does factorise. You might think it doesn't, but it does. It does factorise. But I'll give you a hint. If I were you, I would be using a 3x3 field, 3x3 grid to work out, to predict and check my answer. This factorizes into the product of 2 trinomials, i.e. three-term expressions, not binomials. So I'll leave you to play around with that on another occasion. So of course, once we can factorize, we can then solve. So let's go and solve these equations. I'm not factorizing that. No, you're right. So I thought of all of these as being quadratic formula questions, but I just want to put in some complexity so that they are having to think carefully about what they're doing with the quadratic formula. So this one, I obviously built it backwards. I started off with my factorization, which by the way is 17x plus 5, 13x take away 3. So that's, I wrote that down, expanded the brackets, and then obviously just gave them the finished product. That's why that's why it's really easy to come up with nice factorizations. So I want them to use the quadratic formula, and I want them to write x equals 46, add or subtract 46 squared, subtract 884 times by negative 15, square root thereof, all over 442, and cope with the fractions and no decimals, and want them to do that, and then end up with whatever we have here, negative 5 over 17, 3 over 13, and then work out how that turns back to the algebraic factors. So that negative isn't very clear, sorry, that's negative 5 over 17. So use the quadratic formula, get exact answers as decimals, and then work out how do I go backwards from, exact answers fractions, not decimals, and then work out how do I go back from the fractions to the factors. If I've got the factor, I know what the answer is. If I've got the answer, can I work out what the factor is? And then the same thing here. So again, doing x is negative root 15, add or subtract 15 plus 4, 3, 10, say plus 120, all over 6. And so we get negative 15, add or subtract 135, all over 6. Oh, and of course 135 is, well, 135 is 9 lots of 15. So it's negative 5 root 5, add or subtract 3 lots of negative root 5 over 6. And then we can say that, then we can find the solutions. And then from the solutions, can we then go on and find the factors? And the same thing for the last one. So they're pretty used to having the factors and then saying what the answers are. This is going backwards. Remember, I'm a big fan of forwards and backwards. This is going backwards. Here are the factors. What's the answer? Sorry, other way around. Sorry. Here's the answer. What are the factors? They're used to going, here are the factors. What are the answer? They're probably less used to, here's the answer. What are the factors? My favorite question, what's the same, what's different about these? And how do we go about solving them? I'm interested in any suggestions you've got. What's the same? What's different? Again, I'm going to do the first one because that's an easy. Okay, x plus 1, x take away 2 is 0, so I can go from there. So I think with the second one, they'll try and rearrange, try and make x a subject, try and make root x a subject. So for the third one, exactly that, yes. So I want to think of this as being something else squared, and then subtract something else, subtract 2, i.e. it's the same as that one, and therefore the factorization, exactly. It's comment in the chat, they've all got the same factorization. No, exactly, they've all got the same structure of factorization. It's just they've just got different x's. They've all got different x's. So the third one, the x is actually x take away root 2. So the factorization is x take away root 2 plus 1, x take away root 2, take away 2, because the x in the third one is actually x take away root 2. And then here, the x here is actually root x. So this is going to be root x plus 1, root x take away 2. And then, of course, that throws up the interesting question about that. So root x plus 1 can't be 0. Remember, the root symbol means the positive square root. The root symbol means the positive square root. And then we've got the third thing there. And then down here, my x is now 2 to the x. So I'm going to factorize this one as 2 to the x plus 1, 2 to the x take away 2 is equal to 0. And I get the same problem. I can't have 2 to the x plus 1 equaling 0. So my fact now doesn't give me a solution. Absolutely, Xavier. Really nice way to tie this in with functions. So your f of x is x squared take away x take away 2, and your g of x, say, is root x. In which case, then this would be f of g of x. Yeah, that's really nice, actually. I must admit, I hadn't thought of that. So you make fx equal to x squared take away 2, and you make g of x equal to root x. And what you've got here is f of gx. You've got that composition of functions. That'd be really nice. Yeah. And then down here, we've got sine x plus 1 sine x subtract 2 is equal to 0, but it's the same factorization. It's just different x's. There's a different variable in each one, but the structure is always the same. And again, then from a solving point of view, you then got the issue that sine x can be negative 1, but sine x can't be 2. Okay, what I'm going to do is, I want to say a little bit about graphs, and then I will just pop back and do those 3 slides about factorization. I'll say just a little bit about graphs for a moment, but I'm slightly conscious it's 6:30, and so you might need to run away. So let me say about graphs quickly. So graph sketching, well, we've done all the work for it. We've completed the square on this. So we've got x take away 3 squared, subtract 8, and then we've got x squared subtract 3 squared, subtract 8, and then here we've got x plus 3 squared, subtract 8, and here we've got x squared plus 3 subtract squared, take away 8. And we thought about the minimum, so we know the minimum of the first one is when x is 3 at -8. The minimum of the second one, well, it's not going to be -8, but it's going to be when x is, there are going to be 2 values, isn't it? Okay, so this is going to have minimum at add or subtract root 3 and -8. That's got minimum at 3, -8. This one has got minimum at -3, -8. And this one hasn't got a minimum at -3. It's got the minimum at what did we say? We had the 0. Sorry, not -8 either, 0, 1. Okay, because the least we can do is make x equal to 0. And then 1 plus 3 all squared is 4. Sorry, 0 plus 3 is not, 0 plus 3 is 3, and then 3 squared is 9, and then 9 take away 8 is 1. So the first pair have got, we've got 1 minimum and 2 minima. And then the second pair, one's got 1 minimum, both got 1 minimum, and then kind of what do they look like? You know, obviously you might want to think about solving them. So what did we say? We said that we said that we could solve that one, and we can solve that one. Sorry, as in equal to 0. We find the x-intercepts, and we can solve that one equal to 0, but we can't solve that one. So the bottom one doesn't cross the x-axis, and it's got a minimum at 0, 1. And so, you know, the first one looks like that. And I do actually, I do recommend the idea of giving them graphs on Desmos or something like Desmos, and saying, what can you explain the features that you see? So why does the green one, why does it look like a W? Why does it have those two low points? Well, because that's what we said, didn't it? We said the minimum were positive negative root 3. And when we've done the solving, we'll realise there are 4 solutions, there are 4 roots, which is what we've got there. Whereas with the second pair, this is particularly the bottom one, doesn't have any intercepts, as it only got that one minimum point. And so can we work out why it looks like that? Why does it not look like a W but just a shifted up W? That's quite hard. And part of the answer is you'll learn in A level how to identify where curves turn. So again, it's another good trailer for A level for doing maths and any further maths next year. It's quite nice to put them all on the same graph and just sort of see what's happening. So you've got the 2 quadratics either side, and then and what happens there is they switch from they're reflected when you change from -6 to +6 they're reflected, whereas with the quartics, changing from -6² to +6² changes all sorts of things about the graph. So a small change had a big difference. But I think the idea of giving them graphs, saying, can you explain what you see, is a really worthwhile activity. So I'll do this in a few minutes, folks, but obviously if you need to go, please do. So same idea, factorize. What does factorize mean? It means rewrite as a product. So I can factorize this as x plus something, y plus, well, it's x plus, well, it's going to have to be that way around, isn't it? So I want to get the 3x and I want to get the 5y, and then that gives me 15, job done. What about the second one? Got to think about the positive and negatives. So I want to take away 3x and add on 2y. So it's plus 2y take away 3x, and then that gives me -6, job done. And then lastly, penultimately, I've got x plus 2, well, must be the same, y struck 3, because it has to be the same because they're the same. But now I've got plus 6, not take away 6. So what am I going to have to do? I'm going to have to add on 12, i.e., I've got to complete, well, not quite the square, because this isn't a square. Really, I'm completing the factorization. It's like completing the square, but it's not really completing the square, because it's not a square I'm completing, it's a factorization I'm completing. So it's x plus 2, y subtract 3, plus 12. So I've got my algebraic product, and then I've got my constant. So lastly, I've got x subtract 1, y subtract 1. That gives me x, y, it gives me subtract x, gives me subtract y, and then add on 1, so to complete it by subtracting 1. So the idea of completing the square, we can extend into what look not like squares. Of course, they are sort of like squares because this has a sort of quadratic feel to it. X, y, x, y, x, y. It's a quadratic in x and y rather than a quadratic in x, which would just be x squared, or in just y, which would just be y squared. So it is a quadratic expression, it just doesn't look like one. And this is lovely because this brings me back to my favorite Diophantine equations. So solve this equation. I've got mn subtract 3m subtract 3n is 0. So I complete the factorization. M subtract 3, n subtract 3, subtract 9 equals 0. So I've got m subtract 3, n subtract 3 equals 9. But I want a Diophantine solution, so I only want integers. So I know that m subtract 3 and n subtract 3 n subtract 3 have to be factors of 9, and that's relatively straightforward. It's 1 and 9, 3 and 3, 9 and 1. Or I suppose we also ought to consider -1, -9, -3, and -9, -1. So there are at most 6 possibilities. M subtract 3 has to be one of those, n subtract 3 has to be the corresponding one of those, and we just go through and solve them for m and n. So for example, the first pair would give 4 and 12. And is that right? Yeah, because 4 12s are 48, and 4 plus 12 is 16, and 3 16s also make 48. I quite like that pair, because that gives me m and n is 0. So 0 is 3 lots of 0. Yes, it is. That's true. That's correct. And then that's another question of the same form. So m is 5n plus 6 over n subtract 1, where m is an integer. Now, so obviously, I mean, presumably n is 2 will work, because then I'll have 1 on the denominator. So n is 2 seems fairly obvious. What about n being 0? That would give me -1 on the denominator. So they seem obvious, but are there any others? So well, let's multiply. So we get mn subtract n subtract 5n is 6. So factorize m subtract 5 n subtract 1 because that gives me 5n. It gives me m. It also gives me +5. So complete it by subtracting 5 equals 6. And so now I've got m subtract 5 n subtract 1 equals 11. And so I've got m subtract 5 n subtract 1 because it's Diophantine, because they've got to be integers, have got to be factors of 11. So nice thing is 11 is prime, so it's 1 and 11, 11 and 1, or I suppose -1, -11, and -11 and -1. And therefore, those are my possibilities, and I just need to check that they are all okay. So it looks to me like, for example, if I chose the first pair, that n is, so if n is 12, then 5 12s plus 6 over 11 is a whole number. 5 12s of 60 plus 6 is 66, and 66 divided by 12 take away 1, 66 divided by 11 is indeed a whole number 6. Phew, it works. So this idea of completing the factorization is really good, for solving Diophantine equations. Oh, right, sorry folks, overrun there. Because I put the thinking time in. I shouldn't put the thinking time in. I should just bang on regardless. So apologies. Thank you very much for your patience. I know some of you had to drop out. That's not a problem. You'll get the slides. So I'll send these to you. Really happy. Amy, you want to stay on for a chat? That's fine by me. If anyone's got any more questions, please stay. Otherwise, have a fantastic half-term break. And I will see you in 2 weeks' time at different times. I sent an email about it. I'll remind you, but I have to change the times for the last sessions, which I'm sorry about. I'm really sorry about the changing the times, but we'll make sure that you still get an opportunity. So have really good half-term breaks. Thank you very much, folks. See you soon. Doug, to be honest, I might just do it twice. I think, to be honest, I'll try and accommodate everybody. It's only 2 weeks. I'll probably just do it twice on the same day. Really will be Groundhog Day. Like, I'll do it 3 times in a week. I have no idea. Right, I'm going to stop recording this now.